be Ashley Millan from the Florida Institute of Technology, and she'll be presenting the abundance and dispersal of cephalopod parallarvae in the Florida current. Ashley?
Good afternoon, everyone. Like she said, I'm Ashley Millan, and I will be talking about cephalopod parallarvae today in the Florida current. So basically, the main objective was to determine the abundance, seasonal distribution, and morphological development of cephalopod parallarvae in the Florida current near Fort Lauderdale. Currently, there is very little data on actual parallarvae and cephalopod life cycles. Most of the research done is in adult cephalopods. Therefore, the data that I'll be presenting today can actually help to identify temporal and spatial patterns of spawning, as well as recruitment for adult cephalopods. So why the Florida current? The Florida current's dynamic environment actually transports an oceanic and coastal larvae and adults. This can play a major role in the recruitment dynamics. The loop current is basically formed by the passing of water into the Gulf of Mexico and exiting to the Florida Straits. This recirculation of water in the Florida current has been found to be very important for the dispersal of cephalopod parallarvae. Currently, the only research done on the Florida current on parallarvae was done 20 years ago by David Goldman. So, I'm sure in all your best mind, you're asking, what in the world is a parallarvae? Well, according to Young and Harmon in 1988, they actually defined it as cephalopods in their post-hatchling sub-adult growth stage. Basically, what this means is that while most larvae will undergo a morphological transition into the adult stage, cephalopod larvae do not undergo that stage. Basically, after they hatch, that's the way the adult will look. The only changes that they will undergo is basically going to be morphological changes. So before I actually go into the distribution and transfer of this type of parallarvae, I just want to talk to you a little bit about the spawning and the hatching process for most taxa. Most taxa will actually deposit clutches of eggs at different locations. These egg clutches tend to be spherical or elliptical in shape, semi-transparent, and they're composed of a gelatinous material. These egg masses have been reported to at least house 1,000 eggs and be up to 4 meters in diameter. Now, the jelly-like material they're actually composed of is very important for both their transport and their actual dispersal mechanism. Basically, while the egg mass floats in the vertical column, once the eggs leave that clutch, they're actually negatively buoyant, so they tend to sink to the bottom. Obviously, this will tend to affect the dispersal mechanism as well as the successful hatching process for these parallarvae. Usually, hatching involves mantle contractions by the parallarvae and the use of a terminal spine. Basically, it's a rigid cartilaginous spine at the end of this posterior mantle. Now, the growth of hatchlings, as well as the hatching process itself, has been known to be affected by several abiotic and biotic things as temperature and nutrient supply for these parallarvae. Now, for the methodology. Here, plankton tilts were conducted at 5 different stations along a 15-kilometer transect across the Florida current near Fort Lauderdale. The actual latitude was 26.188 north, and these were done by bi-monthly cruises from late December 2006 until November 2007. As you can see here are the actual locations of the 5 stations. In order to collect these species, what we did is we pointed the boat itself towards the south, therefore the current flowed north, and that allowed us to have an actual stationary position for the collection. Now, the collection was done using the University of Miami's F.G. Walton Smith research vessel, and 2 different nets were actually used in order to collect this parallarvae. The first one was the Tucker trough, and basically this allowed us to have a depth stratified sampling for these parallarvae. Basically, it went through 3 depths, 0 to 25 meters, 0 to 200 meters, and 25 to 200 meters. The second net used was the bongo net, and this is just the depth stratified one, so it just went down to the depth and back up. Now, for methodology, plankton samples were sorted for actual parallarvae, and the initial identification was done looking at their patterns in morphology, as well as their chromatophores and pigmentation. And these were defined by Sweeney et al. In 1992. Now, I must note that the actual identification of these larvae is very, very difficult. Even experts have very difficult time trying to figure out species because of their similarities in chromatophore and morphological characters. Thankfully, Dr. Michael Vecchione, who's the director of the NOAA Systems Facility at the Smithsonian Museum, is an expert in cephalopod biology and is a very good paralogue identification. So basically, after the paralogue were collected and identified, we actually looked at their mantle length in order to determine their developmental stage and know how long they had been actually in the water. The mean density was also conducted, but I'll go through that as we go through this. So a total of 622 specimens were collected and determined to be between 7 different taxa. The 7 different taxa, 2 of them, which are actually were octopi, while the rest were squid. First, we had Octopus burei, which is the brown-striped octopus, Magitrichthys lephalippi, which is the Atlantic long-armed octopus, Abralia verani, the Atlantic squid, Onychicuribia, the tropical pop-hook squid, Onychoteuthis banksy, which is the common pop-hook squid, and Pterygotheuthis and Histoteuthis species. Basically because they are very difficult to identify, at least for these 2 taxa, we couldn't actually pinpoint the exact species for these. Now, I will actually go through only the 4 most abundant species because of time restraints. But here, basically, I have given you the seasonal abundance of cephalopod paralarvae collected during 06 to 07. As you can see, it's very apparent that Abralia and Onychia were the most abundant of the species. Now, the mean density of the paralarvae were actually calculated by the number of paralarvae by 100 meters cubed of water. As you can see, here you have all the species and all the months and year, and it's very, very apparent that in July, September, and November, the mean density for these paralarvae actually increased. Now, like I said, I'll be going through the 4 most abundant species. The first was Abralia verani, with a total of 311 specimens. 168 of them were undamaged and were used for mantle length measurements. Although these paralarvae, most of the species were actually collected all throughout the year and recorded, which can indicate continuous spawning, their peaks basically was in the month of July with a 0.549 per 100 meters cubed. Now, 50% of the paralarvae were actually collected at the surface, 0 to 25 meters depth. The most abundant mantle length size class was 1.5 to 2.5, as indicated by this diagram over here. Basically, 1.5 to 2.5 is what we expect to find for actual cephalopod hatchlings. Second species was Onychicuribia. Onychia had a total of 161 specimens, and just like Abralia, it had the peak in the month of July with a 0.226 per 100 meters cubed. Just like Abralia, you're going to start seeing a pattern here. It was collected at the 0 to 25 meter depth, and the most abundant size class of mantle length was 1.5 to 2.5, indicating again that they were new hatchlings. Now for Octopus burei, we had a total of 44 different specimens, and their actual peak in abundance was during May with a 0.069 per 100 meters cubed. Again, the majority of the specimens were caught at the 0 to 25 meter depth, and the most abundant mantle length was 1.5 to 2.5, as indicated by the diagram. Our last species is Magitrichthys lephalippi. As you can see, it's a very cool looking specimen. It's actually the long-armed octopus because their 3rd arms tend to be proportionally larger than the rest. We had a total of 33 specimens, and these also peaked in the month of July with a 0.050 paralarvae per 100 meters cubed. Again, the majority of the specimens were caught at 0 to 25 meter depth, and the most abundant dorsal size class was 1.5 to 2.5 millimeters. So in summary, a total of 622 specimens were found to be actually between 7 different taxa. 2 of them were octopi species, and the rest were squid. Abralia verani and Onychicuribia were the most abundant, accounting for 50% and 26% of the total species, respectively. Most paralogi were reported throughout the year, indicating continuous spawning. Aurelia, Onychia, and Macrotrichthys peaked in abundance during the months of July. The average dorsal mantle length for those species was 1.5 to 2.5, indicating that these paralogi were captured shortly after hatching. The majority of the paralogi were collected from the surface layer. Now, in conclusion, the Aurelia burani as the most abundant species is actually congruent with the study I told you that was done 20 years ago, where the family Anophthalmophidae were found to be the most abundant, which contains the Aurelia species. Now, it's very, very important to note that the second most abundant species for this study 20 years ago was the members of the Almostrepid family. Not one single paralarval specimen from the Almostrepid family was found in our 622 samples. We really don't have an idea why this is, but we do hypothesize that it has to do with the oceanography and the actual environment of the ocean. Basically, it can strongly influence the transport of this paralarvae, and it can also cause decadal timescales in abundance for different species. So again, this data can help us actually look at the distribution and temporal spatial patterns of spawning, as well as look at possible places where we can actually find the cephalopods. In conclusion, more sampling needs to be done for paralarval specimens in order to actually determine the life history of most of these cephalopod specimens. That's the only way that we can actually determine why we're seeing this shift in transport and abundance. So now, acknowledgements. I would like to thank my mentor, Dr. Jonathan Schenker, basically for the opportunity of working with my passion and the coolness that is the cephalopod paralarvae. Dr. Michael Vecchione from the Smithsonian Museum, without whom I wouldn't have my species identification. Brian Spencer for the awesome pictures you saw up there. And the captain of the crew of the RV Walton Smith. Funding was provided by Suez ADR. See the references? Any questions?
Do you have a hypothesis for why you're seeing some species peak in July as opposed to other months? Does it have to do with a preferred temperature or food
Yes.
source?
Basically, a lot of studies show that the spawning events tend to cause because of temperature. So the higher the temperature for most species, not all, will actually cause a peak in their hatchling. They will hatch faster and more at the same time. So it could be due to those two. Obviously, I only talked about 4 different taxa, but we had pterygiopteuthids and histioteuthids, as well as onychoeuthids, Scancy. And these actually peaked during November and March. But we found so many little specimens that we really couldn't determine the actual distribution and abundance. But yeah, we basically are thinking that it's temperature based. Now for their actual dispersal, like I said, we really don't have an actual idea. So that's where the data will come into fruition. If a person that was good at modeling for oceanography could actually come in, input the data, and maybe we can actually work on why we're seeing this spatial abundance.
This was collected in 2006 and 2007?
Yes, bi-monthly cruises.
So were you on the boat?
No, sadly I was not. I was off campus, so I didn't experience that. I actually did the work with the paralarvae. I'm the first student at Fortech to actually tackle paralarvae. So basically I did all the research. Sadly I wasn't even enrolled in the school by that timing.
So, all the specimens, they were in alcohol?
Yes, yes. Basically all the plankton samples were numbered by the stations. That way we knew how to keep track of them. And I actually had to sit through over 400 bottles of samples and go each by each with tweezers. It was a very interesting process, but it got done. Sadly, I couldn't participate in the actual plankton tours themselves.